All right, so chapter 4, trigonometric functions. And we're going to be learning a lot about trigonometric functions today. But first, before we go over that, the week 3 homework. So does anyone have any questions on the week 3 homework or something they didn't understand? I'll go ahead and pull up the week 3 homework so we can all take a look at it together. Week 3 homework, I believe, was over exponential and logarithmic functions. So any questions over exponential and logarithmic functions? There's a link there. There should also be a QR code up there. All right, so these were the problems that you got. So following, you got 4 problems. Solving logarithmic equations, you got 4 problems. Solving exponential, and then we have compound interest, 2 problems for compound interest. Anyone would like to share their answers, you can go ahead and do so. We're going to go ahead and get started reviewing the answers. So for these solving logarithms, I'd like you to go ahead and remember your properties of logarithms. And these are all the properties of logarithms that you're going to need to know. Not all the properties of logarithms you're going to need to know, but for this purposes of these problems, these are very important to know. So part 1 answers. For log x minus log 2 is equal to 17. It's easier to keep it at 2 times 10 power 17. It would be a very large number otherwise. Number 2 would be x is equal to 5 by 4. Number 3, x is equal to 100 by 3. And number 4, x is equal to 20. Let's go ahead and check your answers. So go back. These are the problems. And these are the answers. On to part 2. So our part 2 answers for 5, 6, 7, and 8. We've got 1 by 4, 2 by 3, 4 by 3, and -1. Any questions on how we got to this answer? Or got to any of these answers? Sorry. All right, I don't see any questions, so you can go ahead and move on to part 3. Part 3 was the compound interest question. The whole question is over here. The whole question wouldn't fit over here. So for this, we used our continuous compound interest formula, in which we use P, which is the principal amount, P of 0, which is the principal amount, E, which is the constant E, to the power of R, the rate in percent, times T, which is the number of years. T will always be recording years and R is always in percent. So in this case, we have 1.99% and 13 years. Any questions on either of these? All right, I don't see any questions, which means we can go ahead and get started on this week's lesson. So this 4th unit will cover graphing, simplifying, factoring, and solving basic trigonometric functions. And you're also going to learn the basics of trigonometry. Some of this will be a review from geometry. And I encourage you to pull on that the geometry knowledge, because we are going to do a few practice problems. So the table of contents for today. First, we'll have the basics of trigonometry in geometry and precalculus settings. Next, we'll be graphing basic trigonometric functions. And then we'll be simplifying trigonometric functions using fundamental identities, and then solving trigonometric functions using these same identities. So these are the basics first. So trigonometry is the study of triangles, and more specifically, the relationship between their sides and angles. And for the purpose of this first section, I believe we're mostly going to be studying right angle triangles. So first is parts of a triangle. So we have the opposite, hypotenuse, and adjacent. So it's important to note that the opposite and adjacent sides are subject to change, because that angle theta is also subject to change. Angle theta could be either this one right here. Hope you can see my cursor. Either this one right here or this one at the top right here, in which case if this is the one at the top, then this would be the opposite angle and this would be the adjacent angle. And I feel it's a little bit self-explanatory. If it's opposite to the angle, it's the opposite side. If it's adjacent, then it is the adjacent side. If it's right next to it, it's the adjacent side. And anything opposite to the right angle in that right angle triangle would be the hypotenuse. Again, this is just a review from geometry, just to get your mind refreshed on right angle triangles. here are some of the basic functions of trigonometry. So we have SOHCAHTOA, if you remember SOHCAHTOA. Sine is opposite over hypotenuse, cos is adjacent over hypotenuse, and tan is opposite over adjacent. It's sine, cosine, and tan and tangent, which are the full names of it, but we abbreviate them like these, like this: SIN, COS, and TAN. This is basically what you learned from geometry. These are the three functions you learned in geometry. You probably had to use these in geometry. When going over trig for precalculus, what we're first going to go over is the unit circle. So the unit circle looks a little bit scary, but here's a representation of the unit circle, and we see cos theta, sine theta. The reason it is called the unit circle is because it spans only it spans up to 1 unit in each quadrant. So I'm going to go back one slide, and we see 1, 0, 0, 1, -1, 0, and 0, -1. These are regular coordinates. We also have degree measures like this. We have 30, 45, 60. But what's going to be more helpful to use in precalculus is radian measures, because radian measures are smaller numbers, and they are generally, you'll find they're a lot easier to work with. It's like going into algebra 2 and not liking fractions, and you liking decimals better, but then you realize the fractions are actually a lot more helpful in algebra 2, and it's the same thing with using radians in these problems. All these pairs, coordinate pairs, these ordered pairs on the outside are just that, ordered pairs. You'll notice that here both sine and cosine are positive. Oh, by the way, it is cosine comma sine. So the cosine of that angle, cosine of 0 is 1, the sine of 0 is 0, 1, 0, and it works the same for the whole thing. So in that first quadrant, you have cosine comma sine, and they're both positive. Second quadrant, cosine comma sine, cosine is negative, sine is positive. And third quadrant, cosine and sine are both negative, and the fourth quadrant, sine is negative and cosine is positive. And you're going to see that when we look at our table in just a second. This is just another representation of it. So you have the sine, cosine, tangent, and then that 1 and the theta over there. And again, cos theta, sine theta. And here are your further trig functions. So the ones we're going to be adding on are cotangent, secant, and cosecant, and they're pretty straightforward. Cotangent is 1 over tangent, secant is 1 over cosine, and cosecant, which is usually abbreviated as CSC, not COSEC, is 1 over sine theta. So you have here that it's 0, half, 1 by root 2, or root 2 by 2 is the better way to do it to rationalize these values. So 1 by root 3 would be root 3 by 3, 2 root 3 by 3, so on and so forth. This is a very important table to remember, so I encourage you to take a screenshot of this or copy it down. Also, just a reminder that these will be on the website. So if you miss something, because this class does go very fast, we've got a lot to cover today. If you do miss something, feel free to go back over these videos on the website and take your notes down. All right. Our first problem, which is just a review of geometry to trigonometry. Problem number 1, to solve for x to the nearest 10th. And I'm going to give you just a couple minutes to do this. Yeah, feel free to use a calculator on this question because it's kind of hard to get an exact answer. Yeah, go ahead, use a calculator. We'll just have one more minute and then we're going to take a look at the answer. This is just a review, so I'm not too concerned about us going over this one. It's mostly the new stuff that's going to be a little bit harder to understand because pre-calculus, trigonometry is, I find generally, is hard for a lot of people to make that shift from the geometry viewpoint of trigonometry to the pre-calculus view of trigonometry. So we're going to spend a little bit of extra time on that today. I see someone with a raised hand. Make sure to keep your hand up if you do have a question. All right, let's see if I can find. All right, go ahead and unmute. If you raise your hand, let us know your question.
Oh, my bad. I didn't know like it was like a question. I thought it was like I was supposed to answer it. My bad.
Oh, okay, yeah. If you want to answer, go ahead.
I got 19.4.
19.4. Okay. You can go ahead and take a look at the answer. It's been 2 minutes. And yes, the answer is 19.4 if you approximate to the nearest tenth. So nice job on that one. Again, this is just a review of geometry. We're going to go ahead and move on to the next one. This will be a little bit more complicated than the one from before. It is a multi-step problem. So make sure you're looking at this. Make sure you know that it's a little bit more complex than the one we just did. It's composed of one right triangle split into two right triangles. You've got values 9 and x. You know that 35 and 61 added up together is equal to 96. Oh, that does not appear to be a right angle triangle. Right, this is not a right angle triangle, but it is split into two right angle triangles. So we've got that 96-degree angle at the top, two unknown angles at either side, and 9 plus x is this base value. I'll give you a little longer to do this. So right now it's 6:17. Let's go about until 6:18. Let's go till 6:20. Again, if you have any questions, if you're confused about how to work this through, we're going to go over the answer in the next slide. Let's just hang tight until then. We've got about 1 more minute before we can go ahead and go over the answer. It may be a little bit of a short period of time, but I do want to get through the rest of the lesson today. So. And make sure to keep your hand raised if you've got a question. All right, it's 6:20. Let's take a look at the answer. Our answer is 23.3. Are there any questions on this? I didn't see any questions when we were working through this, which means this should be clear, just basic trigonometry, and we can go ahead and move on to the next section. All right, so our second section, when we get into the pre-calculus view of trigonometric functions, and we're talking about graphing various trigonometric functions. So trigonometric graphs are very unique in their shape, as sine and cosine graphs are oscillating, and they represent the values given as outputs in a certain trigonometric function. So we'll take a look at sine and cosine functions, just analyzing the way the function looks as when it's written down. First, we have f of x is equal to a times sine, and then in this case, it's sine times k times x plus c, close parentheses, plus d. D is that vertical shift. The amplitude, it's important to know the amplitude is the absolute value of a, and the period is 2 pi over the absolute value of k, and the phase shift will be negative c. If you remember that from our transformations lesson, negative c, it would be negative c. The plus is the plus makes it a negative value. So if you were to have in the final equation of your graph, say x plus 8, it would move left 8 units. If you were to have x minus 8, it would be moving right 8 units. We remember that from just transformations. So here's an example of some few sine functions. They're characterized by oscillations between a y value and its negative and the parent passing through the origin. So some examples are f of x is equal to sine x, which is the parent function you see passes through the origin. The y value only goes as far as +1 and -1, and it has an infinite domain. You also have in g of x, we have 2 sine x, and now the y value, it looks the exact same as the parent function, except the y values only go as far as -2 and +2. And we have a much more complex function as the last one. We have 4 sine, which means if that was just added on to the parent function. Let's go ahead and open the graphing calculator. I'll let you take a look at this for a second while I open the graphing calculator. Let's go ahead. Again, I do use Desmos. It's a very good substitute if you don't have a graphing calculator at home, but let's go ahead and get to our. So we have y is equal to sine of x. So this is our parent function. I'm going to go ahead and make this a little bigger. This is our parent function. Y is equal to sine of x. If we just add that vertical stretch on, y is equal to, actually I'm going to do these all separately. Y is equal to 4 sine of x. And you see it extends from +4 to -4. Y is equal to sine of half x. And you see that just widens the domain of that function. Let me go take this one out. Y is equal to sine of x plus pi by 2. And again, that's just that phase shift. Y is equal to sine of x minus 1, and that's the vertical shift. So you see these all hold that similarity to the parent function. Let me do, lastly, we have our completely 4 sine times 1 by 2 x plus pi by 2 minus 1. And you see that looks vastly different. So you have this characteristic, but the reason that this one goes to only 3 and -5 is because of this, that shift down by 1. You also have the characteristic of that, the graph being stretched out a little bit more, and then you have the shift left with that. These are your first function and the final function. All right, let's take a look at the cosine functions now. The cosine functions are structured similarly. We have the characterized by the oscillations between a y value and its negative again, and the parent passes through 0, 1. We have cosine, the cosine of x, 2 cos x, and 4 cos of half x plus pi by 2 minus 1. And that's just similar to this, except got the cosine. Well, let's take a look at that. Just look at it's the same graph. The only difference is, again, that stretch. You see here, same graph. The difference is now the horizontal stretch. I'm sorry, the horizontal stretch. Now you have the shift, the phase shift. It's important to know the know the terminology for that. So phase shift, vertical shift, horizontal stretch, amplitude. We've got the amplitude change from 1 to 4 here. Phase shift, vertical shift, and then our final graph. And then we take a look at tangent functions. So tangent functions are a little bit different. They're characterized by they've got a restricted domain and an infinite range. With that change in continuity that you see it, and the parent function, it goes right through 0, 0, goes right through the origin. So it's the same thing with this. I don't believe we have enough time to go over it in the graphing calculator again, but I encourage you to just take a look at Desmos on your own time at home and put these equations in it, turn the colors on and off, and try to match the differences. See if you can split these equations up into all their different transformations. Now for the reciprocal functions, we've got the cosecant functions. The secant functions, which are very similar in shape to the cosecant functions. And the cotangent functions, which just look like a mirror of the tangent functions. So sine parent function, cosine parent function, and tangent parent functions are just sine x, cosine x, and the tangent of x. And obviously we have the cotangent of x, cosecant of x, and secant of x. So this is a good representation of all these graphs together. We've got tan theta, cos theta, sine theta, secant theta, y, cotangent theta, and cosecant theta. Theta is usually used to be a placeholder, like we have x as a placeholder for some value that you plug in. In trigonometric functions, we have theta that is a placeholder for an angle usually. If you put in, I'm not sure if they have a theta here, but I'm sure they do. Hold on. Oh, they've got it, yeah. Cos theta. You see, and you get the same thing as y is equal to cos x. It just looks the exact same. One's just theta and the other one's x, so it's not really that big of a deal. All right, and now we have our sine and cosine transformations. So f of x is equal to sine x. Amplitude, again, is equal to the absolute value of a. The vertical shift, horizontal shift, phase shift, frequency, period, and and it's important to know these things down because they're going to come in very handy when you're analyzing all these functions. And here is a master chart of all the various sine functions. Here is basically an introduction to the identities. Here's how you represent cosine in terms of sine, how you represent tan in terms of sine, how you represent cosecant, and how you represent sine in terms of cosecant. I'm sorry, I misspoke. Yeah. So how do you represent sine in terms of sine, cosine in terms of sine, and cosecant, or sine in terms of cosecant? Yeah. So go ahead and take a screenshot of this. It might take a little too long to note this down. So I encourage you to take a screenshot of this, and it's very good for reference. Another thing you'll really want for reference is the unit circle. The unit circle is the holy grail of all pre-calculus references. You're going to be using it a lot. So I suggest you print out a copy of the unit circle, understand it, highlight whatever you need to, make whatever annotations you need to, and keep it with you for the rest of your pre-cal career. Now for our quick exercise, we're going to find 3 x and y values and use a calculator to approximate these values to the nearest hundredth. Just pick one of these, as usual. Just pick one of these 3 equations to find 3 x and y values for. If you want to read them out by raising your hand, if you want to put them in the chat or in the Q&A, make sure you put which question number you do. We've got f of x is the first one, g of x is the second one, h of x is the third one, or if you want to reference them by f of x, g of x, h of x, that's not a problem either. This shouldn't take too long, so we'll take about 2 minutes for this. So it's right now 6:30. At 6:32, we can reconvene. Got about 1 more minute. All right, it's 6:32. Does anyone have any answers they'd like to share? If not, I'll just go over one of these. So any answers you'd like to share, raise your hand, chat message, Q&A, anything works. If not, I'll go ahead and start working on 3 tan times 4 x minus 3. So let's go ahead and take an x value. In this case, it's just a simple act of plugging in x values, because you're not going to get the pretty values that we talked about in the last few classes. You're not going to get that with these specific equations, because I didn't write them in that way. So let's pick a value for x. Let's say x is equal to 0. 0 minus 3 is equal to negative 3. Times 4 is equal to negative 12. The tan of negative 12. Oh, I forgot to mention, tan of negative 12 in, let's go with radians. So tan of negative 12 in radians is about 0.635 times 3. That would give us about 1.9, and I would approximate that to a 1.91, which you could graph as 1.91, or if you've got a graph with not as many divisions, you graph that as just 2. And then we can go ahead and put in 1 minus 3, negative 2. Negative 2 times 4 is negative 8. The tan of negative 8 in radians is 6.799. And times 3, we'll get that as 20.39 or 20.4. And then, of course, we can just do 3 minus 3, 0. 4 times 0. Tan of 0 is 0. 3 times 0. 0. So we have 3 comma 0, which would be our x-intercept. We can go ahead and move on. So here's something that you can do really, really quick. It's 6:34. I'll give you just 1 minute to do this. Find the attributes of the following function. It's just one value for each one: amplitude, period, and phase shift. So right now it's 6:34. At around 6:35, we'll give, actually, I'll set an alarm. 6:35 or 1 minute. We'll go over the answer for this. So timer. 1 minute. All right. The amplitude, the period, and the phase shift. Remember, the phase shift is 2p over k. Sorry, the phase shift is, let's go back. The phase shift is the negative c, sorry, and the period is 2 pi over k, and the amplitude is the absolute value of a. So let's go back to that. Got 30 seconds left. Ten seconds. All right. Let's take a look at the answers. So we have for our amplitude. Oh, sorry. Yeah, the phase shift in this case would would not be that. Okay. The phase shift in this case would be 9 because I put in that -18, but regardless. We have amplitude is 4 because the absolute value of -4. The period is pi because we have 2 taken over here, 2 pi over 2, which is pi, and phase shift, which in this case would be negative of -18, negative of -18 by 2, which would be 9, just positive 9. All right. And now we can go ahead and move on to part 3, which is simplifying an identity, simplifying trigonometric functions using these fundamental identities. And first, we're going to go over the identities. Here's a quick note: memorize the identities. They will come in handy. It actually takes a lot longer for you to keep looking back and forth between a sheet of identities and your homework. So just generally on homework, whenever you're trying to work on any problems, like in class or anything at all, just memorize those identities. It becomes so much easier, it comes a lot faster, and it comes in handy not only when you're doing a verifying identities problem, but also when you're solving or are simplifying and such. So here is your list of identities. This is not by any means a master list. This is not everything you need to know about trigonometric identities, but this is just the major ones that you're going to need to know for the purposes of the rest of this class. But in your later pre-cal classes, you will definitely be using the rest of the trigonometric identities. So right now what we find is a lot of importance is the reciprocal identities. We know cosecant is 1 by sine theta, secant theta is 1 by cos theta, and cot theta is 1 by tan theta. And you have quotient identities. Tan theta is sine theta by cos theta, cot theta is cos theta by sine theta. Those two are very important. I find that I use them a lot. And the Pythagorean identity, in which the only one that you really need to know is that sine squared theta plus cos squared theta is equal to 1. And your sum and difference identities, which are listed below. And it's probably best to know all of these sum and difference identities. They can come in very handy if you're just trying to find the exact value of a trigonometric function. And these double angle identities, I don't believe we'll be using, but they are also very, very useful. So go ahead, take a screenshot of that, or just note down the names of each section so you can find them later. And again, these videos will be on the website if you want to revisit them. Now, surprise, we're going to be recalling a couple identities. So I'm going to go ahead and say the name of an identity, and I want to know like what it equals or what it would be categorized as. So 1 by sine theta is equal to what? You can go ahead and put it in the chat, raise your hand and answer the question, or put it in the Q&A. 1 by sine theta is equal to what? All right, I got an answer. It is cosecant theta. That's correct. All right, 1 by cotangent theta. 1 by cot theta. What is that equal to? Yes, it is tan theta. Good job. That's correct. How about cos theta by sine theta? Cos theta divided by sine theta. That's correct. It is cotangent theta. And let's see. We'll have 2 more. What is the most important Pythagorean identity that you need to know? just mentioned this one. I said it's basically the only one you need to know. Comes up a lot. Got an answer, is it correct? Ooh, you missed around the order. So it wouldn't be cos squared theta plus sine squared theta, or I suppose it doesn't really matter. Yeah, so yes, it would be sine squared theta plus cos squared theta. I find it easier to remember it as sine squared theta plus cos squared theta. And yes, you are correct. It is equal to 1. One more, pick a sum identity. Okay, so sine of a plus b. What is sine of a plus b? Correct. It is sine a cos b plus cos a sine b. Great job recalling those identities. Okay, so we're going to go ahead and move on. Those are some of the most important identities you're going to need to know. And this was just a quick test, but of course, take some time and to memorize these identities. It's very important. All right, so now we're going to go into verifying identities. Verifying identities is sort of the pre-calculus. It's a proof. It is basically a proof. It's a proof to show that the left side is equal to the right side, to show that these trigonometric identities are in fact true. So here we've got about 4 steps to break down trigonometric identities and verify identities. So first what we want to do is analyze the equation. So we check for representations of the fundamental identities. If you see on one side that it says sine squared theta plus cos squared theta, and the other side says something like 1, we'll say we have sine squared theta plus cos squared theta, and then some other term, and then the other side has 1, and then that same other term, you can immediately say, okay, that's equal to 1, and you can just do it just one step. You can verify that identity, and be very thorough when you're looking at this with the identities in mind. Second is to pick a side. So play to your strengths. If you find simplifying easier, I would start from a more complex side, usually with 1 fractions. And if you find expanding easier, you can work from shorter, simpler terms. I generally tend to see that simplifying is a lot easier for a lot of people. So for most people, I would say definitely start with simplifying. So start with the fractional larger values in your trigonometric identities. Also, break down fractions very carefully. You may not always need to break down a fraction, and that comes into handy when you're thinking about those quotient identities. Let me go a couple slides back. When you're thinking about these quotient identities, and sometimes people will break down sine and cosine, and sometimes you don't want to do that because then you can get straight to tan or straight to cotangent, and it's a lot easier that way. So again, watch out for representations of those quotient identities that could be very useful. Keep the other side in mind as well. So don't forget about the other side, and only work one side at a time. That's if you remember that about proofs, you can only work one side at a time. Don't work both sides. It's not a proof anymore. You're not verifying the identity anymore. So when I say don't forget about the other side, I mean that don't start making a sine value into a tangent if there's no tangent on the other side and just doesn't lead you anywhere. So think about the functions that are on the other side when you're verifying these identities. So here's a quick one. We'll take about 3 minutes to do this. This shouldn't take too many steps. Verify that the following is equal to cos theta. And also, when you're verifying the identities, make sure you go through every single step. And that means like every single step. If you've even got 1 plus cos theta and the other side says cos theta plus 1, that needs to be another step. Cos theta, like make that order right. You need to put every single step when you're verifying these identities and when you're writing that down. I tend to see that it works a lot easier if you work vertically. So if you just work in line after line, do the first step in one line, second step in one line, like we saw in this previous slide, it just works a lot easier and you're able to just follow your process a lot easier. So it's 6:44. In just another minute, we're going to go ahead and look at the answer, walk ourselves through verifying that the following is equal to cos theta. All right, let's go ahead and take a look. verify that the following is equal to cos theta. So we started with secant theta minus sine theta tan theta. And so we can change that secant theta using our reciprocal identity to 1 by cos theta. And tan theta can be changed into sine theta by cos theta. And now we have 1 minus sine squared theta over cos theta, which is cos squared theta. If you remember that from the Pythagorean identity, which is sine squared theta plus cos squared theta is equal to 1. So 1 minus sine squared theta is equal to cos squared theta. So cos squared theta by cos theta is just equal to cos theta, and you've successfully verified your identity. All right, so now that you know how to do that, let's go into solving. So solving trigonometric functions using these same identities, using these same skills you've been going over. Note, take caution when solving. So you always use these identities to simplify. If you have a very, very large value, it's not going to be easy for you to just know the trigonometric value that quickly, especially since a lot of trigonometric values are going to be decimals or complex radicals or something like that. So use these identities to simplify, and it makes things a lot easier. So here's our example when we're solving using identities. Differences first, this is not like verifying. You can and should use both sides when you're working. In this particular example, they chose not to use both sides, but generally you should use both sides when you are solving a trigonometric equation. Number 2 is to remember your fundamental identities. So they are among the most helpful. Also remember identity properties, and that you can multiply by 1 if needed. And you see that in the third step here. They broke down 1 into 1 minus sine x over 1 minus sine x, which can really make things a lot easier. And that gives you here 1 minus sine squared theta, which they simplified into cos squared theta. And so again, there's your fundamental identity, your Pythagorean identity. Do not simplify into numbers. So that's an important one. Keep numerical values out for as long as possible when you're solving. So don't just say, oh, I know that cos x is equal to this. I know that when cos x is equal to this number, x is equal to this number. Like it's just not helpful for you, and it's a lot easier to find. You'll just put yourself into trap. So definitely don't do that. Simplifying soon, again, might complicate your process. Keep values small. If you do end up using any numerical values, keep them small. If you have like bigger numbers, usually when it gets into 3-digit numbers, I'd say stop making them into numerical values and just continue on with your identities. And simplify into simplest terms, which you see right here, and it works very, very well. So what they've done is they've simplified these two terms here into a simplest term, which is just 2 by cos x, and then you can easily solve a problem. Again, radians is usually your friend when you're doing this. All right, so we can take a look at this for another quick minute. And this might take a while, so go ahead, take a couple minutes, solve this. We'll get about, let's say, 3 or 4 minutes. Let's do 4 minutes. 6:48 right now, and I'll set an alarm so at around 6:52. All right, time starts now. I'm actually going to cut this short at 1:30, so we have time to go over, we have a little bit more time for one of the more complicated problems. But here is the answer you should have gotten, not necessarily the method you would have done, but it's the answers you should have gotten. Tan squared x minus 3 is equal to 0, tan squared x is equal to 3, tan x is equal to plus or minus 3, tan x is equal to positive 3, and tan x is equal to negative 3. And in the case of tan x being equal to positive 3, you get x is equal to pi by 3 radians, or x is equal to, in the case of negative root 3, x is equal to 2 pi by 3 radians, or 60 and 120 degrees. And usually when you're taking a test or a quiz or doing a homework assignment, it'll usually be specified that they want the answer in radians or they want the answer in degrees, so I wouldn't worry about that. But also on that topic, remember the domain of your answer. Use the unit circle for reference if needed. So sometimes the domain of the answer will say something like only values from 0 to pi by 2, and pi by 2 is 90 degrees. So 0 degrees to 90 degrees. 0 is less than x is less than pi by 2. And so the only answer here that would be the correct answer is pi by 3, and 2 pi by 3 would be extraneous. So remember to keep that in mind. If it says just solve for all possible values of x, it's easier to just do these pi by 3, 2 pi by 3, and just add 2 pi n, in which n is equal to all real integers. I believe it's all real integers. And it's a Z shape that you would draw, just like, looks something like that. All right, so let me clear that up. Let's go ahead and move on to the next question. Solve this one using identities. So 3 cos of 2x plus sine squared of x is equal to 0. And here we've got our, let me go back. Double angle identities. Cos 2 theta is equal to cos squared theta minus sine squared theta, or 2 cos squared theta minus 1, or 1 minus 2 sine squared theta. So write one of those down so we can go back to our problem. We're going to take a couple minutes to do this, so at around 6:55, we'll go ahead and continue. So yeah, that Z value would be integers, where n is equal to any integer. All right, let's take a look at the answer for this one. So they simplified that into 3 times 1 minus cos 2x by 2 plus 2 times 2 sine squared x cos x by 1, and that is equal to 0. And then that breaks down to 6 1 minus cos 2x plus 2 sine squared x. This is a very complicated way to go about it, but the answers you would have gotten is x is equal to pi by 2, or x is equal to plus or minus pi by 3. And you see in this case they put k, but the representation for that is usually n, so 2 pi n, where k is an integer, or you can put your answer can be written as, let's say the answer is say pi by 2. So we have pi by 2 plus, let me write the x is equal to. So you have x is equal to pi by 2 plus 2 pi n, and then a little semicolon, n belongs to, so that's how you write the little belongs to, all integers. And it's that funky looking Z shape. That's how I would write an answer when there is no domain given. So would anyone like to share the way that they went about solving this problem? And if there's nobody, that's fine, because we are going to take a look at the next slide, which is today we learned. Today we learned the basics of trigonometry in geometry and pre-calculus settings, graphing basic trigonometric functions, simplifying trigonometric functions and using fundamental identities, and solving trigonometric functions using those identities in various domains, in restricted domains and in the infinite domain. So we do have homework. This week's homework is, this week's homework can be found with this link, https:/bit.ly/week4 precal, or you can just go ahead and scan the QR code. I'm gonna go ahead and pull up the homework so we can look at it together. Just a minute. Let me pull it up in viewing mode. And this homework, even though it's not necessarily going to be due and we won't necessarily be going over it, it's very, very useful. It's got all the skills you need to know. It's just generally a really good practice worksheet for pre-calculus. So here you go. Let me share. So let's take out this. Yeah, basics. So the basic section to fill in the following table with exact values, radian values, I might add. Find the following values using sum and difference identities, which is not something we went over in class, but it's something that, so you take this number and you use the sum and difference identities to add the degree values from this table together, and so you can find an answer that way. Fill in the unit circle with exact values, and I would probably not use this specific unit circle for reference. I would print out my own annotated unit circle. That's however I like it. Unit circle is very useful. Complete the following trigonometric identities, which is just sort of filling out the trigonometric identity. Sine theta is equal to 1 by cosecant, cot theta is equal to 1 by tan, so on and so forth. And right triangle trigonometry, just some basics. Graphing, and I've got all the directions here. Find the amplitude, period, radians, phase shift in radians, the vertical shift, and the minimum, max, and values. Then sketch the graph using radians. You've got fundamental trigonometric identities, and you use the identities to find the value of each expression. Verifying the identities, and these are just very, very simple identities to verify. It's nothing super complicated. And you've got about 10 problems to solve, and two more. These two, I believe, are in, these two are in the domain of zeros less than theta is less than or equal to theta is less than 2 pi. And this one is just all possible solutions. So that's what we have for the homework today. Also, I would like you to fill out this survey. It's just talking about your experience that you had at this summer session of Kid Teach Kid. The link is down there, https://kidteachkid.org/student-survey, or you can go ahead and scan the QR code for the survey. And I really encourage you to fill this out. It's very helpful in helping us understand, how you enjoyed this, where you're at. I want to thank you all again for attending these sessions of pre-calculus. I hope it's been really helpful for you, and I wish you all best of luck when you take pre-calculus class. So thank you, and I'll hand it over for the next class.